Yo, yo, what's up? Today we're working on my x86 operating system, written for fun, nothing too crazy. Right now it's in a kind of good initial state where we can initialize some like memory, we can work with like heap allocations, we can work with the clock, and we can work with interrupts that like will trigger a sleep that will put the CPU into like a halted state. When the interrupt runs and we like know that we've waited for enough time, we keep track of that and we wake it back up. That's kind of like our demo right now. It doesn't really do much. There's no like real main loop yet. We just kind of initialize drivers and like run this demo. Where I want to get eventually is like the ability to run some form of like web server. So what we're doing right now is we're trying to work with PCI and make sure that we can read and write to like a network card, and then we're going to try to figure out how to like get network working in general. So last stream we kind of got to the point where we could read and write, or I shouldn't say and write. We could like read the MAC address, and we kind of did some like initial investigation and did some like probing, and we now have like a pretty decent understanding of how the system works. Let's quickly pull up the OS Dev Wiki for the network card I'm using. So it's this guy, RTL8139. So this is a PCI network card. He's plugged in, and the first thing that we're going to do today is we're going to try to like update our port allocation system to try to like make this work a little better. And then once we've like kind of figured that out, we'll know that our how to say this, sorry. Yesterday we did like some initial investigation. We kind of have like a good enough idea of how to work with PCI now that we can kind of like make a proper PCI module with PCI subsystem and like get that hooked up into our kernel initialization into our demo. And once we're there, we're in like a pretty good spot to like checkpoint, commit, and like have a chunk of work that's like ready to merge. And after that, we can try to like actually get into like the nitty gritty of the network card and see if we can get some like reading and writing going. So that's the plan for today. So the reason we want to do this like port allocation update or port management update or however you want to call it is there are these lines going to the CPU, and it goes to like RAM, which is where we work when we're doing like any memory, like storing anything. Pointers go to this, right? So the pointer gets to like encoded as like 32 bits or 32 lines of addresses, and then these guys kind of like go and multiplex their way into like individual cells in the memory blocks or whatever. But these guys also go to IO. And the way I was thinking of this before is that like every combination of lines interacts with like one thing. So you have like one thing here, one thing here, one thing here. And each of these things were like 1 byte, right? One address, 1 byte. But I'm finding now with PCI that that's not the case. First of all, some of these guys kind of come out like this, where they have 4 lines going to one chip, and you're actually only allowed to read this chip, like one specific. You're not allowed to read like halfway into this. You're just reading like, 32 bits from like one address. I think that's not actually quite right. There might be like read and write. I'm not really sure how it works. But the idea is that like, one, there are non-single byte elements, and 2, if I look at like the register table for this card, EEPROM, where's the register table? Register table, come on. Is this it? Default value. It was in here somewhere. One sec. Media status register. Okay. Is this it? Configuration register? Somewhere they had like a map of all of the registers. It must have been up before all of this. Before this. Here we go. If I look at the register table, there's offset 0 all the way down to offset 00DH. So there's like a range of addresses we can actually think of these as that you can read from. And if I were to like try to allocate one, like ask the, how to say this? Right now we can only like get access to a single byte. And so if we were to try to get access to like all of these individually, it would be a pain in the ass. Here, let's show the port manager, right? Like right now we just have this like request port, and he takes in like one address and he gives me one port, I called it, that I can read and write to. And so what I think makes more sense now that we know that there's these like really, really big chunks of memory that kind of like belong to one device, what makes more sense here is it takes in an address and like a length. And this now allocates like a range that we can work with. And maybe, yeah, no, that's good. So we'll get a range, right? And then instead of like allocated ports, we can have like allocated ranges in here. And we'll have to find some way to like mark these as allocated. And then what we need to do is instead of like these ports that we have that you can like, this will return a port, but instead of like writing just directly, we'll have to write to like an offset, right? And all of these will have to take in an offset. And these guys will have to like validate that they're not going out of the range that they're allowed to work with. So they'll have a length in here. Length usize. Right? And that should be good enough. So that's step one, is try to get like this API kind of worked out in a way that you can just kind of like allocate ranges and read from those ranges appropriately depending on how your device driver wants you to. So I think the first thing we have to do is figure out how are we going to like track these allocated ranges. And we need to do some sort of like overlapping range check, right? So you have like a struct range. We actually have range structs built into the Rust language. So let's see if Rust has like ways to work with them that can check like, oh, does this overlap with that? So let's see, we have range inclusive, range core ops range inclusive, start equals end. So this is close. So what do we have here? We have range full, unbounded range, range from range. This is what we're looking for. This is like the normal. Did that say yeet? Why? What the fuck is this? Do yeet expression? There's no way that they're calling it that. Absolutely no way. I'm sure that this has a meaning that isn't just like yeet and throw it, but I want to know. Sorry, I'm just distracted now and I need to know. I need to know. From residual ops. What is this for? Tracking issue for standard related to this, which now means ops yeet. Throw. No way. No way. They're actually putting the word yeet in as a replacement for throw in the language. That's insane. What the fuck? Why would you do this? This is such a meme. Okay. Okay, we'll sorry, getting distracted. Okay, so we have a range type in the Rust standard library. And he has, if it contains an item, okay. Good. Does it have like an overlapping range? Bump, 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 bump. Looks like not that I can find, but it's also really easy to implement if they give us access to the start and end, right? Which they do, they're public. These do have to be of a type IDX, but that's okay. And let's just check, like, let's do a quick find for like overlap or, yeah, okay. I guess we could see if this like contains if the item is contained in the range, and I wonder if you like can pass in another range. Impl IDX. No, because this has to be an index. Okay, that's fine. So what we can do is we can have a list of ranges. So that's core. Let's see, it was ops range. And here we can say that this is a range of U size. Or I guess this should be a range U16 because the addresses are in U16. And these should actually probably be range inclusive because at the very end, the last element, like U16 max, should be valid. And so saying if we have range exclusive, we have to go one past U16 max to mark that, and that's a problem. So we'll use range inclusive. And then we can say what goes in here. Request IO range, we'll call it. Maybe I'm not even really convinced that calling this ports is right anymore. This is really just more like another memory space almost from my perspective at this point. So I might rename this later, we'll see. So to request, we'll first keep the old mechanism in so that the initial implementation will be easier, and we'll implement this in how do I say this? We'll implement this through the new way, right? So we can say that we have this request port, and he takes in an adder, and he returns an option port. And he now, hold on, let me think. He now returns self request IO range, which with adder and length 1. Easy. Now, really, in order to support the like offset encoding here, we're going to need without like breaking all call sites, we actually will want to keep these old ports this way, and we'll want to make new ports that use the offset thing, and we'll do the same thing. We'll wrap the new ports with the old ports. So let's start there. I guess also what we should do is eventually we'll have to write some tests for these like range allocations. They're a little difficult, but that's fine. And so now we need to replace this like allocated ports with these allocated ranges. So we should say for range in self-allocated ranges, we like check that range is not used. So we'll have like is new range if ranges overlap, and we'll have the range that we got here and our adder plus length like this -1, right? Because we're doing inclusive ranges. Return none. Otherwise, we insert the new range. And really, these ranges don't have to be hashes anymore. These can just be vectors. A vector. Probably. Because we don't need to like track. These can just like be linearly stuck in now. It doesn't matter because we're iterating over all of them every time. We don't have to do like these like intelligent lookups or anything. So let's use alloc vec here. Okay, so if the ranges overlap, and really this could be like all wrapped in a function like, let's see, range already allocated. And we'll take in the allocated ranges, which is a slice of range inclusive U16, right? And new range is a range inclusive. And this should be by reference like this. This returns a bool. And this guy all goes in here. So ranges overlap range and new range. Return true, else we return false. Okay, so we split this out now into like its own little helper function, and really we should probably write a unit test for this eventually. So let's first write this function. Function ranges overlap range new range, and this returns a bool, and this is a range inclusive t. Really, these don't have to be specific to U16s. And arguably, these should be split out somewhere in like a utility class, but I think that it's fine to just write them here for now. Maybe in the future we'll see that we want them, but that's fine. And really, I was going to say that these don't have to be for U16s, but since we're writing like our specific case right now and not worrying about like generic code, we're not going to like add the extra complexity. Okay, so we can return range dot end. So what are our two cases though? These are like linear overlaps, right? So we have like this is good, this is bad, this is bad, this is good. So if both the start range.start and is less than okay, sorry. I was going to say we have to check if both the start and the end are outside, but we can assume that these are like incrementing ranges. So we actually can just say if range end is greater than less than new range.start, or new range.end is less than range.start. So that's the two cases. Is that the only two cases? What about new range? Yeah, is that really it? Let's think about this. No, because what if... Do I actually have to draw this out? Okay, so we have range 1. This is always end on the left. And then we have this and this. And are those really the only two cases? Because there's this where start is less than end, and this where start is less than end. But here, start is also less than end. So we have, sorry, end is less than start. End is greater than start. End is greater than end. Start is greater than. I think it really is just these two cases. That's kind of surprising to me. And unfortunately, I struggle with this enough that it's worth unit testing just to double check. So we'll just do a config test down here, and we'll make a module test, and we'll say use create testing star. So we have like our own unit test mechanism here, because we can't run like normal tests through main because we're in a kernel in like virtual machine. So we have these like test runners that we've set up manually through this like nightly feature in Rust. So that's why I have to import this, and we use super star to get access to like our functions that we added here. And we have this like create test macro that sets up our tests for us, and we'll call this like test overlapping ranges. who should return okay initially. Let's see if we can compile. We actually can't compile right now, so we'll just stub this out. And we'll just write unimplemented. This. Okay. So why aren't our unit tests running? I probably broke them yesterday. No, something's just totally fucked. Let's see what we've done. Oh, it's because we're panicking in this request port. So we should just leave the old... we need the old code back before we get crazy here. So let's git show source port manager. IO port manager. Yeah, nice. And we can just copy paste this old version back for now. Because we want to get like we want to keep the existing code intact and then do like a one-off switch at the end. So here we paste this guy in and we delete the changes we've made here so far. Okay, cargo run. Does our, well, no, because we forgot something. What is it mad at? Use the name ASM is defined multiple times. Oh, here. Okay. Cargo run. Okay, we run. Cargo test. Do we test correctly? Yes. And we have, in fact, where is this? Test overlapping ranges is passing now. And so now we can just write in a test failure to see that that also correctly works. And we need to do into here to make them a string. And that does, in fact, fail. Okay. So now we can start getting into actual implementation of the tests. So we just want to make sure that ranges overlap like 0 to 5 and 5 to 10. So first we want to make sure that this is not true. And we want to make sure that 0 to 5, 4 to 5 overlaps, and 0 to 5, 6 to 10 doesn't overlap. So these should actually be true, because they're testing overlap, not non-overlap. And we'll swap the order, so 6 to the 10, 0, 5. And that's probably sufficient, I guess. I'm not really too concerned about it. We need to borrow these. So we just stick these guys like this. And like this. Jesus, what an absolute shit show of brackets. I don't like this. Okay, so let's just check these ones first. Cargo test. So 107, it doesn't like this. So this is actually flagging that they don't overlap, which is a problem. Because these actually need to be less than or equal to, because we're using inclusive ranges, not exclusive ranges. And 108, it doesn't like that now. So here we have 0 to 5 and 4 to 5. These definitely overlap. So why is this not working? So 0 to 5, 5 is less than range.start. Aha! So if end is less than new start, so in this case we have 5 is less than 4, or new range.end is greater than range.start. Or is... So this is where... This is backwards. God damn it. This should be range.end is greater than, or new range.end is greater than range.start. Is that correct? No. Let's go back to these wonderful diagrams. So these overlap in what cases? I was doing the non-overlap cases, which was a mistake. So this overlaps in this case, where start is less than end and greater than start. Or this case, where end is greater than start. Right? So that's just if range start is greater than or equal to new range dot start and range dot end. Oh, and the start is less than or equal to new range dot end. This is one case, or the same thing but with end. Okay, let's try this again. Cargo test. There we go. He's passing now. And we can just do these guys as well, where I need to put borrows here, and brackets, and brackets. Okay. Let's see, is this good? Cargo test. Yeah, okay. So it actually is a good thing that I went through this because I actually had it fucking wrong. What a surprise. What a surprise. I assume that this can be simplified, but I'm okay with this for now. Okay, so now let's replace allocated ports with allocated ranges as a vec of range inclusive U16, like we said before. Allocated ranges is default. This should still compile, and we can say request IO range instead of request port, like we said. So request IO range with adder and length. And then we can say if range already allocated, so we can say let new range is adder plus length, right? And this has to be inclusive range. So the length, we need length minus 1 to be the last element is not like, we're not doing like for I in 0 to less than length. We're doing less than or equal to, which means that we have to subtract 1. So we can say that if range already allocated in our allocated ranges, we can pass in the new range. We do not allocate the port, so we return none. Here we need to borrow, so that doesn't go away. And here we need a semicolon. Otherwise, we push this in and say push new range. We clone it, I guess, probably. Maybe it has copy, we'll see. And then we just return port adder for now. Okay. Yeah, that seems reasonable. Cargo test. Okay, so now let's make a new struct port range, which is very similar to port, except it contains an adder and a length. I guess theoretically, length should also be a U16, not a U size, because we only have U16 address space. And here we'll do the same thing where we have read L, write L, read B, write B, which is like read a long or a Boolean. Let's actually name these write U8 and write read U8. I like those names better. And this will be called offset. So we're gonna write to this offset this value. Is that a reasonable way to do this? You could argue that, how do I say this? I often fuck up these types of APIs. And so what I often will do here is I'll make like a new struct that's like port address or port offset, we'll call it. And he takes in a U16. And the reason to do this is just to make sure that like the type system enforces that I get this right. So I can just say port offset U16 here, and the value is just a value. So this needs to be public for that to work. And I don't know if I have to write pub here. I can't remember. We'll see. We will see. Okay. So now the first thing that we have to do here is self. So these can now fail, right? Because you can punch in an invalid port offset for this port range. So these will now return results where on success it says nothing, and here we say port offset out of range, and we'll make a struct offset out of range that derives debug and error. Error derived using this error no std macros that just simplify the like debug, display implementations, etc. And we can just say error provided offset is out of range. And maybe we'll even put in the valid range. Given value like this and valid range like this, and this guy can take in U16, U16, U16 or something. Something like this. Let's say this guy might actually be a more complex struct that says value start and like this. Start, so we need to be passing the value, start, and end. I think that's a reasonable error message. Provide offset is given offset. And maybe we don't actually need start because the offsets are 0 in base all the time. So we can just say range, like length. And we'll say max offset length. There we go. This doesn't need to have an underscore. This is a human message. Cool. Cool. Okay. So now what we have to do is we have to, in each of these write and read functions, check that the offset is valid. So we'll have a function, so first of all, this isn't port, this is port range. And we'll have a function, is offset valid? Right, and we'll take in this guy, presumably by reference, but actually we can take him in by value and say that this guy implements clone and copy as well, which should be relatively free because it's a U16. Oh, oops, this is the wrong derives. This guy goes here, and he doesn't derive error. He does derive clone and copy. Okay, so we check if the port offset is valid. And maybe this guy just returns a result offset out of range. And we'll say verify offset. So then in each one we can do that makes it like nicer than returning a bool of true or false, because then we can just do self verify offset like this instead, with a question mark to like return the error, instead of trying to do a fancy like if then return error blah 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 blah, you know. Okay, so what doesn't he like now? Candidates define as impl cargo check. Oh, okay, so I need to return self here, or take in self by reference, and then unimplemented to say, please Rust, please compile, I beg you. And this guy now needs to return okay at the end. Okay, so we've got our like stub right. And we'll just have to do this same transformation to all of these. So verify offset, what's he going to do? He is going to take in the offset, and he's going to say, this actually isn't enough. We don't only need the offset, we need the length of the write. Or, what do I want to call this? Length? Length is so generic, like operation or bit width, we'll call it. What's the bit width for this? Or num bytes, we'll say. That seems reasonable. And so here, we can say if the offset plus num bytes is greater than self.length, greater than or equal to self.length, is that right? Okay, sorry. So what I'm trying to do here is I'm trying to say is if I execute a read at this address, am I going to go out of range? And so here I'm going to have this range that is like inclusive 0, exclusive length. And here, if I actually read at length minus 1, that's valid. But if I read at length, that's not valid for a 1 byte read. So this should be greater than self.length because the +1 makes it okay. Is that correct? So let's think about this. Let's say our number of bytes is 4. So if our length is 12, or 16 we should say, that means bytes 0 to 15 are allowed to be read. And if we read 12, we can do a 4 byte read at 12, 13, 14, 15. And so 12 plus 4 is 16, so we can actually, which is valid. So we can say if this is greater than self.length, not greater than or equal to. Return error offset out of range. Else is okay. And here we say we're doing a 1 byte read. Okay, or a 1 byte write. Here, we're going to say, this actually takes a value and a num bytes and a length, which will need to be in our error message. So we're given offset with reading num bytes at, but we have a max offset of length. Okay, so now we have to actually define this error, which is value is offset.0, num bytes is num bytes, and length is self.length. Okay, I think we're chilling. So now we do the same thing here where we read U8 at offset, port offset, and we return a result of U8 or offset out of range. We can now also verify offset 1 here for a U8. And then here we return OK read. Cool. And now we do the same thing here where we say we want to read it offset, port, offset. We're writing a value of U32. So we have self, verify, offset, offset, and 4 bytes this time because this is write 32. And here we return a result of nothing or offset of range. Okay, like this. And read 32 does the same thing, but we do it at offset, port, offset. And we return a result U32 offset out of range. Okay, we return okay here. And now we're chilling. Cargo check. We compile, and probably we should like test verify offset. So we call this test verify offset. This seems quite complicated. I think it's not too bad. All I'm doing right now is like doing some like sanity checks. I think any individual piece is actually quite manageable, and you just kind of like build up the required knowledge over time. There's nothing that like all we're doing really in reality is just reading and writing values. So like we just have RAM or numbers that we can access, and all we're doing is like being like, what's at this number? What's at this number? If these were like cells, what's at this number? And we're just trying to like add some safety mechanisms to make sure that like two drivers aren't talking to the same number at the same time. But like all drivers are essentially just this. Like you have some numbers or some locations in memory that you can write to and read to, and let's just interact with those. It's actually much simpler in my mind once you get over the first little hurdle than doing something like working with like any closed source library is like the same, right? You have documentation, you're trying to do what the documentation says, you're trying to probe to make sure that you understand the documentation correctly, and all of that just it's all the same. It's just the documentation is now reading and writing specific memory addresses instead of making specific function calls. Yeah, feel free to stick around if you want to see where we go. Okay, so we're reading and writing. Am I doing it for fun? Yeah. Fun is a twisted word in my mind. But yeah, fun. We'll call it fun. Okay. So we're reading and writing 32 bits here. These functions are now right, and we wanted to test that our verification, that our overlapping ranges are okay. So, or not overlapping ranges, are address limiting. So we can call port, what do we call this here? This is a port range. So let range equals port range, and we'll give it off adder, it doesn't matter, so we'll just give it 0, or maybe like 50, just for shits and giggles. And its length, it will be like a 24 byte range that we've allocated. And let's just see if we say range verify offset, let's say that we want to read 1 byte at address 50 plus 23. That's an edge. So this should be okay. So test, I wonder if there's, I have this like test true, but that doesn't really like work here. So like the way that we would need to test this is, maybe we test that these two things are equal, and it's range verify off, oh shit, did I delete something here? Yeah, I did. Test EQ, we want to make sure that these things are the same, and the range, and okay. Right, this should allow this right. And if we write our tests, we need to add a semicolon there. And here, it's going to complain at me because these guys don't implement EQ, the equal trait, so we can just add these here for testing. Cargo test. So here I need to wrap these in port offsets so that I don't accidentally to punch in the wrong thing. So port offset here. Cargo test. It doesn't like the, oh my god, what a stupid fucking, I would think that the type system should be able to figure this out, but I guess not. So let's, instead we'll make a test true macro like this. And in testing, or not test true, we'll test okay and test error, we'll call it. So test okay will, he will run a match statement on the expression. And if it's okay of anything, he'll return nothing. Otherwise, he will say, he will return an error, and in this case, that's this guy. So he'll return a, what is, oh, here we're returning file line A is not okay. And really, this doesn't need to be a match statement. We can do like if equals a, like this. Okay, I think this is right. If oh, we should say a is error. There we go. There we go. That's what we want. And did I fuck up my brace matching? This guy, we don't need this match anymore. That's what we're missing. Okay, so now we can test okay. Oh my god. So we delete all this. Cargo test. And he actually doesn't like that. So offset out of range 73, 1, 24 is not okay. Oh, because I'm not allowed to do 50 plus here. Okay. And test that 24 is out of range. And so now we do the same thing, but instead of test okay, we have is okay is not error. Very nice. Okay, so those pass now. And now we want to do the same thing, but with bigger ranges. So we should test that this is an error if the read length is 2 bytes. And we should test that this is an error if the read length is 4 bytes. 21 to 4 should go over, but 20 to 4 should be okay. So let's try that. And all those pass. So we have validated our address ranges fine, which means that we're actually in a good spot to commit a checkpoint. Right? And now what we want to do is we want to start using these like new versions of our port allocation in the rest of the system. So we're actually going to say that request IO range actually returns a port range, right? Port range, which is adder and length. And now we can implement port in terms of port range. So we can replace this guy with inner of port range. And all of these guys now are going to be implemented in terms of the new thing. Delete, delete. So write B is inner self.inner.write U8. You make me remember another guy who also did his own operating system and streamed it. Good old Terry David. Is that the Holy C guy? Terry David. Canadian actor. That's not the guy. Operating system. Yeah, he's the Temple OS guy. Terry Davis. You were off by 1 letter. Yeah, I've heard of this guy. He seems a little crazy, but also people really liked his operating system. I've never really ever looked into it, but it seems like kind of fun project to like dive into. Probably wasn't that fun for him. But yeah, pretty cool stuff. Okay, so here we're implementing our ports in terms of the new thing. So we write U8 with the port offset of 0 always, and the value gets propagated. And we'll just unwrap these for now because we don't actually expect, we're not going to be using these long term. We're just trying to like make incremental progress towards this like new version of the API. And so these guys can just use unwrap for now. And if they fail, they fail. And our OS will crash, but that's okay. Write 32. And this is read 32. Okay, cargo. Then this probably doesn't compile because here request port now needs to be implemented in terms of self request IO range, which is adder and length of 1 always. And it will return this like port range thing. So we just need to return, we need to like change that into port like this, the like wrapped thing. Okay, cargo check. And he's pretty useful there. We need to make this public. And we can delete these allocated ports now. We don't use this. Which is a deletion here. Cargo check. Hash set. There we go. Okay. Cargo run. So does this still compile and run? No. We actually don't like that. So we're getting an invalid right here where we tried to write the value 0 for 4 bytes of length 1. And this is actually probably correct because our PCI implementation was in fact fucking up this. And that's why one of the reasons that we're writing this. So let's try to find those PCI reads and writes, and we'll just replace those ones specifically with the new version. So, or I guess we can just comment out all of this PCI shit. And then this should work. Okay. Sick, sick, sick. How come I know so much of this off the top of my head? So one, I wrote everything in this operating system recently, so it's all kind of just like right fresh in there. And I would say that before starting this, I didn't, right? It's just, there's a lot of reading that I do kind of like in between streams, and that helps me come here with like enough knowledge to write something, but not enough knowledge that I'm just like rewriting something that I've done before. Okay, so that does work. And so now we have this like port allocation ready to go, and we can just quickly, we can start replacing this with the IO ranges. So here we're going to request an IO range at CF8, and these were 4 bytes if I remember correctly. Let's take a look. OSDev wiki PCI. So the two 32-bit IO locations are used. The first location is here, and the second location is CFC. So CF8 and CFC. And presumably these are adjacent to each other. What's 8 plus 4? Is that C? 8, 9, 10, AB. Yeah, so these are two adjacent. So I can actually call this PCI range, or PCI IO, we'll call it, is 8 bytes at CF8. So the first 4 bytes are the config address, and the second 4 bytes are data. And so here we take in a port range, and we'll say this is PCI IO. And then we'll just have to like slowly work through all of these. So first of all, does this compile? Probably not. Probably not. Yeah, because there's a lot of stuff inside this class that we're using the data port directly. So here, maybe inside this guy, we'll make some like constants for config, PCI, config offset is going to be a port offset of 0. And I can't initialize this type because it has private fields, so I could either just expose this U16 to the world, or I could make a wrapper function to initialize it. So let's do that. Const pub const function new. He takes in a U16, so values U16, and he spits out a port offset, which just is port offset U16 val. And then back here, I can just do new instead of that. Okay, and then I have the data offset, which is 4. Okay, so now I can just replace these usages here with self.pci.io, which write 32 to config offset, and then I do a read of 32 to PCI data offset. Seems reasonable. What doesn't it like? He doesn't like that. Oh, I'm using. Why did I use port manager here? That was stupid. I need to import this. So port manager. This also needs port range, like this. Okay, and do we compile? Mispatch types expected U32. Found result. Okay, so here for now we'll just unwrap again. For both of these. And then I think this compiles. Cargo check. Cargo run. Nothing crazy happening yet, but we're not doing anything yet, so it makes sense that we're not compiling or we're not crashing. So let's try this part where we got the PCI or the address of the network card. We did this yesterday, and we just need to make sure that this all still works. So let's just run this and see what happens. So he doesn't like that. That's great. Let's start bisecting where the problem is. So probably here. Yeah, this find device stuff doesn't work anymore. So he's calling config read, where he writes 32 bits address and reads at PCI data offset. So I wonder why he doesn't like this. Oh, it's unwrapping a none value. So that's actually not these. These are errors. It's an unwrap maybe of this guy. Yeah, so he's compiling and running. And if I take off this unwrap, does it like not crash? Yeah. Okay. So why does this find device all of a sudden not work? Did I fuck this up when I converted? Git diff. So in main. Okay, so let's see what we found here. Before we had 0xCF8 and 0xCFC as data port and or as config port and data port. Now I'm writing to 32 bits of address to the config offset, which is 0. So this should still be CF8. And I'm reading. Oh, fuck. Did I fuck up these functions in PCIO? This write 32. Ah. This needs to be self.adder plus offset. All of these places. Whoops. Whoopsies, whoopsies, whoopsies. Cargo check. Cargo run. Rookie mistake. Yeah, I know, man. I know. Okay. So now these functions are not crashing. We are back in the state where we were in before, I think. So if I unwrap here. Yeah, nothing's crazy happening. No crashing. We're chilling. And so probably now I can just uncomment everything here about like Mac reading from yesterday. And I got a little too excited there because when I work with the IO of the RTL or the like network card, we're in the same situation. So here I still need to request IO range instead of a port. And let's just say for now, we're going to request 8 bytes. This still needs to be as U16. And we don't need like port 1 anymore. We just have the RTL IO, we'll call it. And so we'll first do a read at port offset 0. And there's a missing thing here with a new function. And this guy is port offset 4. Port offset new 4. And RTL IO. Okay. So before we pulled the first 4 bytes and then the second 4 bytes individually, and we're still doing that now, but we're just doing it with this new API that we just wrote. And here we probably have to unwrap these because these are now failable calls when they didn't used to be. Okay, cargo run. Okay, so we're back into the state where we were before. So I think that we can call this like update port allocation system to support port ranges. We can call that done. And probably I'll want to back out. I'll want to like remove the old version of these, but I'll probably do that off screen because there's no real good reason to just have you guys watch me change APIs everywhere. So let's do this now. We'll get commit -m PCI drivers now can be allocated. PCI drivers is wrong. We'll say PCI IO ranges can now be correctly allocated. Okay. So the next thing we want to do is we have like an idea now of like what PCI initialization looks like from what we just experimented with yesterday. If we want to like correctly hook this up to the driver now, it makes sense to take all this like experimentation code that we had in main and move it out of main and into like a proper PCI subsystem, and initialize that in the kernel driver. I'm just gonna quickly flag a time on here so I don't forget it later. This is like approximately 1:01-ish into stream was when we finished that. Okay. So let's start doing that. So if we're going to have PCI, it probably makes sense to split a module. This is like, I've been putting everything that uses IO, like these like IO memory buses into like the IO module. I think that's like not really right, but I'm just going to follow that organization structure for now. So we'll add another module that's called PCI inside the IO module. And in here, we can do something like start copy pasting this PCI stuff from yesterday in here. So I'll just do like a blanket copy paste first, and then we'll kind of like review the code and see if it's what we want. We'll just blanket copy all imports for now to make sure it compiles. And we'll let the linter remove those later. And now in main, since we've deleted all this stuff, we now need PCI probably. Cargo check. And he's going to get mad because there's... What's he bitching about? Private structs, undeclared types, not accessible. So there's like private public stuff that we got to fix up and clean up. And in PCI, we're not allowed to use the IO module directly. Okay. So this can just go in here, port offset. Okay. So this guy needs to be public. This needs to be public. This needs to be public. And basically every function in here for now needs to be public, and we'll kind of figure out later if we actually want all this stuff to be exported or not. But right now it's being used directly from main, so main has to be able to see it. Cargo check. Do we compile now? We didn't get them all. We didn't get them all. Pub. We're closer. PCI device, and we need to import this from main. So in main, we need IO, PCI, and PCI device. Cargo check. And he doesn't like this. We need to add a function now to like inject the PCI IO ports into the PCI. So we'll say plug function new. IO is a port range, right? And he returns a PCI now. So he goes in like this, and we put PCI IO. Maybe like this. Okay. And now we can use new PCI-IO like this. Cargo check. Okay, we're compiling again. Solid. Cargo run. And we're running again. Okay, so now the question is do we like where we ended up with this like PCI stuff? So let me just quickly try to clean up some of these warnings. So git add -u, git add PCI rs, and we'll git commit and say happy smiley face. And then we'll run cargo clippy fix allow dirty, and that will clean up a lot of these like import errors. Okay. Okay. Let's clean this up a little bit to get rid of these warnings, just to make it a little happier. Okay. So review time. So we have these like config and data offsets into the port range. I think that's fair and correct. We have a struct PCI, and then we immediately go into this like PCI address stuff. So this should be separate from that. And maybe it makes sense for the first thing that we see in this file to be the PCI definition itself. Or maybe it makes sense to build it up the other way. So we see the... no, this is right. Okay. So we get like a PCI. And this takes an port range, and we can like read a bus slot function and offset from these guys from here. Sorry, one sec. The question is, do we want this to be like directly accessible by anyone? This probably doesn't have to be public right now. I don't think anybody's reading this directly. But we do have this like find device function. So our PCI device drivers pass in like a vendor ID and a device ID, and they just walk the whole bus and look for that vendor and address by reading the config bits on each of them. I think that's fair. And I think that's like a fine API. And he returns a PCI address. And I don't know if I like that name, because PCI address, what does he do? Is he has a read register function and an upgrade function. And does it really make sense for anyone to be calling these? So this upgrade is when we look at like the PCI configuration, there's this, let me see if I can find it. One sec. Where is the header? God damn it. Header type 0. Yeah, so there's this header field in like this like common PCI header. So we talk to the device and we say like, hey, what are you? And he'll tell me like his device and his vendor ID and a bunch of like other metadata. And one of the things he says is like, what am I? And if you like look at this header type, it like expands into like these 3 separate types of devices. So we have this like upgrade function to take us from a PCI generic or a device that can read this common header into one that can read like the specific header. And so really, probably external users of this class, the PCI subsystem, I don't think they actually need to do anything with the common header for now. And so we can leave this PCI address as like an internal implementation detail. And we'll just return the like PCI device directly here. So here we'll return PCI device. Up, and we'll just call upgrade on this guy. Like this. And now the types are wrong. So instead of an option here, we can say result option. And the reason that we would want to do this when really there's no reason, how do I say this? Even though these are both just flagging like yes or no, we have the thing, stacking them is actually valid here, because if there's no PCI device with this vendor and device name, there's nothing like failed per se. We just didn't find it. Where if we found it and it didn't return like one of the header types we expect to see, that's like an actual problem. And so saying like option result gives us like the distinction between those two concepts. So I think this is an option result, and I actually want a result option. So I think there's a way to just like invert these two, if I remember correctly, in like the Rust docs. There's some form of like switch result option to option result, which is kind of like a weirdly specific API to have. But we'll take it. So option. We'll see if there's a way. Transpose. Here we go. Transpose. There we go. And this is okay, none. So does everything compile still? No, because previously we were manually upgrading in main. So in main now, we can say that our RTL device is just this find device, and we'll double unwrap it. RTL device, we'll call this. And so now this has to be renamed to RTL device. And PCI device doesn't have find IO base. That's surprising. I thought it did. So let's take a little peek skis. Aha! So here we have this like PCI device, which is like, hey, you could be either the general or a bridge or bus. And here we're actually still in this state, and we have to unwrap it. So just give me 1 second. One second. Here we go. So here, we need to match this. And if this is a general PCI device general, we return that. I like to use V here for value. And otherwise, we'll panic and say RTL device not general as expected. Okay. Cargo check. Do we compile? We're close. RTL general is not found in this scope because this is RTL device now. RTL device. Okay, we compile. Do we run? We run. We print the MAC address that we passed in still, 1, 2, 3, 4, 5, 6, 7, 8, BC, 9A, BC. And nothing's crashing. Everybody's happy. So I think that that's like a pretty reasonable split out here. I think that I'm happy with that API for now. And we'll let it evolve as we start typing, you know? So let's status get add-u, commit, checkpoint, PCI module split out. And this is at around 1 minute and 13, or 1 hour and 13 minutes in the stream. Okay, so now we have this like functional PCI driver that we implemented mostly yesterday, but we split out today. And we now need to like hook this into the kernel. So in our kernel structure right now, we don't have much, right? We have somebody to track time, somebody to track sleep, someone to like handle IO for us, and like this RTC driver. Let's now just kind of shove a PCI subsystem in here. And for now, we'll just assume that no matter what, since we control the execution environment of our operating system, because we're only running it in a virtual machine right now, we'll just assume that we always have PCI. And I think that that's probably a reasonably valid assumption for all x86 PCs that I would ever run this on, because I'm not going to run it on any, only QEMU. So now we move this like PCI initialization into our kernel initialization. So let's just comment all of this shit out real quick. And it's weird for kernel main to be the one that's allocating this PCI, or like the port range. Really, the PCI subsystem is the one who should know what he wants. So instead of taking in this port range here, he's actually going to take in the port manager. And this is a create or port manager, we can just say, and we'll use create IO port manager. And we'll move this range over request over here. Now that this is a like proper API, we can say we can return a result that says, what does this guy say? Request port IO range. What does he return? He returns an option. And it kind of makes sense that if I request a range from the port manager and he doesn't give it to me, that might be like expected behavior, right? There's two things that can happen. Either it's there or it's not. And so it saying we don't have that available right now isn't an error. But if I'm trying to instantiate the PCI subsystem and it's not there, that's actually a problem. So we'll make a error type that's like, what should we call this? PCI ports unavailable, or PCI IO unavailable. And he will derive debug and error. And his error message will be failed to allocate PCI IO range, which I think is a fair error here. And so now we can say result. This is a PCI or a PCI IO unavailable. And here we have to put this in an OK. And here, I think it's like OK is the OK or. Here we go. PCI IO unavailable. Okay. So it's getting mad that this error macro isn't available, which is true because I haven't imported the this error module in this, or the this error macro in this module. And probably it's getting mad at main because I have to here say expect failed to initialize PCI. Eventually, I'm going to make this like kernel initialization properly propagate errors. Properly propagate errors. But for now, I'm not going to bother. So we just write that we failed and we'll know why, or we can dig into it later. Okay, so PCI is now initialized as part of the kernel, and really our like network card should be part of kernel initialization as well. But for now, let's kind of, we'll run this. How do I say this? We'll run this like demo stuff right now as external to the kernel. Oh, wait, what am I saying? I want to put this in the demo. That's what I want. So the demo now. You're going to sleep? All right, have a good one, Dave. Catch you later. Hope you come back. Okay, so my demo now, it does some sleeping, it does some CMOS stuff, and probably here, we'll just initialize this, the network card here. So this is the network card, we grab it, this takes self PCI now, and self.port manager, self.pci. Okay, are we chilling here? I think all of this should work. We'll make this an unsafe demo because I don't want to bother with writing unsafe wrappers everywhere. And cargo run. Okay, and now let's just kind of like simplify these. This demo messages are getting kind of nasty. So let's just say MAC address received through port IO, or we'll call this IO space, because I don't know what it's called. And we'll say let mac equals RTL IO like this. We need to read the first four bytes, and we'll actually make this a vector. Mac dot extend, I think, is the word for what I want. No. So we'll make this a vector, and then we'll say we get the value, the first 4 bytes in little endian, and then we'll say mac push. Is it push back or just push? I think it's just push. And we'll do we'll call this, like, what do we call the received value here? Val 32. Oh gosh, what's a word for this? This is like the first 4 bytes that we pull out from a little endian read. So we'll say this, we'll call this first 4, I guess. And we'll say this is first 4 and 0xFF, or get bits. Offset from 4, we want 8 bits for a byte. And we'll just do this again, where we do 8, 16, 24. I think it's like this. And what doesn't T like now? Expected one of, exclamation point, blah, 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 blah. Found comma. What the fuck is he talking about? This is Alec vec new. Let's see the expanded error in cargo check. Oh, it's because I wrote mac dot comma push instead of mac period push. Cargo check. He doesn't have the type get bits because I'm not importing my my fancy utility class here. So util, this is bit manipulation get bits. And I have to stick a comma in there. Where'd it go? Get bits, comma. And then I get the second 4 is this offset 4, and I back push second 4 dot get bits 8 bits again. And here we go. So now if I print the mac here, I should be able to say something like print with x's question mark and print mac. Cargo check, cargo run. Yeah, there we go. 1, 2, 3, 4, 5, 6, and now I can do the same thing where I can say MAC address received through memory space is just this. Cool. So our demo now is reading data from a PCI device through both mechanisms. And that's a good checkpoint. So PCI device ready, demo ready. No, network initialized in demo. Okay. And now the last piece is we need to start like stubbing out our network card driver. So the first thing here is to stick it into, like, create a new module and a new type for it. What I like to do here is I like to start by stubbing out in just like in main, so that before I get a feel for what the driver is going to look like. But I'm kind of thinking about what the next steps are. So the next steps are split out the driver and start trying to like use the driver to work with interrupts. But I think that that's going to require more time than I'm going to put in today. So I think that this kind of makes like a natural stopping point where we got here, and we'll pick up on attempting to do transmission and receiving of data tomorrow. So thanks for tuning in. Anyone that's stuck around can catch me on YouTube if you want to catch up. And if you're on YouTube and you want to catch me live, I'm streaming most days at around 2 PST, or I should say Pacific time, because I don't know if it's daylight savings or standard time ever. So yeah, thanks for watching, and I'll catch you on the next one. Bye.